26 light-years away from Earth, there is a planet with water. The James Webb Space Telescope just detected water vapor in the system of JJ486b, a rocky world that orbits so close to its red dwarf star that it completes one full trip around in just 1.5 Earth days. But here's where things get really interesting. Scientists are not entirely sure where this water's coming from. Is it hiding in the atmosphere of this scorching hot planet, making this one of the most important discoveries in the hunt for life beyond Earth? Or is the water trapped in cooler regions on the surface of the star itself, fooling us into thinking we found something groundbreaking? This mystery is what we are going to explore today, and trust me, the answer could change everything we know about planets beyond our solar system. Before we dive into the details of this discovery, let me set the stage for you. Imagine a world that is 30% larger than Earth and 3 times heavier. Picture a place where the surface temperature reaches around 800 degrees Fahrenheit, hot enough to melt lead. Now imagine that this world is locked in place, with one side forever facing its star while the other side remains in eternal darkness. This is JJ486b, and it is one of the strangest planets astronomers have ever studied. But what makes this planet truly special is not just how extreme it is. What makes it remarkable is that the James Webb Space Telescope detected something unexpected there: water vapor, and that single detection has sparked one of the most exciting debates in modern astronomy. Let me take you back to the moment this discovery was made. Scientists pointed the most powerful telescope ever built toward a small, dim red star called JJ486. This star is not like our sun. It is cooler, smaller, and much fainter. But orbiting this star is a rocky planet, JJ486b, and this planet passes directly in front of its star from our point of view here on Earth. When that happens, some of the starlight filters through the thin layer around the planet, if there is any atmosphere at all. The James Webb Space Telescope captured that light and broke it down into different wavelengths, creating what scientists call a transmission spectrum. And in that spectrum, they saw the signature of water vapor, but almost immediately questions arose. Was the water coming from the planet, or was it coming from the star? That uncertainty is the driving force behind everything we are going to discuss today. To understand why this discovery matters so much, you need to know a bit about the planet itself. JJ486b is what astronomers call a super-Earth. That means it is bigger than our home planet, but smaller than the ice giants like Neptune or Uranus. It has about 3 times the mass of Earth and is roughly 30% larger in diameter. If you could stand on the surface of JJ486b, you would feel gravity pulling you down with a force much stronger than what you experience here on Earth. Walking would be difficult and jumping would be almost impossible. But standing on the surface is not something anyone would want to do for another reason: the temperature. JJ486b orbits incredibly close to its star. It is so close that it completes one full orbit in just 1.5 Earth days. To put that in perspective, it takes Earth 365 days to go around the Sun. This planet does it in less than 2 days. That proximity to its star means the planet is blasted with radiation and heat constantly. The side of the planet facing the star is scorched to around 800 degrees Fahrenheit. That is about 430 degrees Celsius. At that temperature, metals like lead and zinc would turn into liquid puddles. Any water on the surface would have boiled away billions of years ago. So when scientists detected water vapor in the system, it immediately raised questions. Where could this water possibly be hiding? One possibility is that the water is in the atmosphere. If JJ486b has a thin atmosphere, it could be constantly replenished by volcanic activity beneath the surface. Imagine a world covered in active volcanoes, constantly spewing gases into the air. These gases could include water vapor, along with other chemicals like carbon dioxide and sulfur compounds. On Earth, volcanoes release water vapor all the time. In fact, volcanic outgassing is one of the ways our planet got its oceans in the first place, billions of years ago. So it is not impossible to think that the same process could be happening on JJ486b. But there is a problem with this idea. The planet is so hot and so close to its star that any atmosphere would be constantly stripped away by the intense radiation. For an atmosphere to survive, something would need to be continuously replacing it. And that is where the debate gets really interesting. The other possibility is that the water vapor is not coming from the planet at all. Instead, it might be coming from the star. Red dwarf stars like GJ486 are known to have dark spots on their surfaces, similar to sunspots on our sun. These spots are cooler than the surrounding areas, and in those cooler regions, molecules like water vapor can exist. When the planet passes in front of the star, the light filtering through might be picking up the signature of water vapor from these star spots, not from the planet itself. If that is the case, then the detection would not tell us anything about the planet. It would just be an artifact of the star, and that would be disappointing because it would mean we are not looking at a planetary atmosphere at all. So which explanation is correct? Right now, scientists do not have a definitive answer. Both scenarios are possible, and both have evidence supporting them. The team that made the discovery used two different instruments on the James Webb Space Telescope to analyze the light from GJ486b. One instrument is called NIRSpec, which stands for Near Infrared Spectrograph. The other is called NIRIS, which stands for Near Infrared Imager and Slitless Spectrograph. Both instruments detected the same water vapor signal, which is a good sign. It means the detection is real and not just a fluke or an error in the data. But detecting the signal is one thing. Figuring out where it is coming from is another challenge entirely. To solve this mystery, scientists are going to need more observations. They are planning to use another instrument on the James Webb Space Telescope called MIRI, which stands for Mid-Infrared Instrument. MIRI is designed to look at slightly different wavelengths of light, and it should be able to tell whether the water vapor is coming from the planet or the star. If the water's in the planet's atmosphere, MIRI should see a specific pattern in the data. If the water is coming from star spots, the pattern will look different, so the next round of observations will be critical. But even if it turns out that the water is coming from the star and not the planet, this discovery is still important. It shows us just how precise and powerful the James Webb Space Telescope really is. It can detect tiny amounts of water vapor in a system that is 26 light years away. That is absolutely incredible. Now let me tell you a bit more about the planet's environment. GJ486b is what scientists call tidally locked. That means one side of the planet always faces the star, while the other side is always in darkness. This happens because the planet is so close to its star that the gravitational forces have slowed down its rotation over time. Eventually, the rotation period matched the orbital period, and the planet became locked in place. The same thing happens with our moon. One side of the moon always faces Earth, and the other side is always facing away. But on GJ486b, the consequences of tidal locking are much more extreme. The side of the planet facing the star is incredibly hot. The surface would be a nightmare landscape of molten rock, glowing red and orange from the intense heat. There would be no liquid water, no ice, and probably no solid ground in the way we think of it. Everything would be melted or vaporized. The other side of the planet, the one facing away from the star, would be freezing cold. Without sunlight, temperatures would drop to near absolute zero. Any gases or liquids on that side would freeze solid. The only place where conditions might be somewhat moderate would be in the thin band between the day side and the night side, a region called the terminator zone. In that narrow strip, temperatures might be cool enough for some molecules to survive without being destroyed by heat or frozen solid by cold. But even in the terminator zone, conditions would be harsh and unforgiving. Despite all of this, the fact that scientists detected water vapor in the system is still exciting. Water is one of the key ingredients for life as we know it. Every living thing on Earth needs water to survive. Our bodies are made up of about 60% water. Plants need water to grow. Animals need water to drink. Even the simplest bacteria require water to carry out their basic functions. So when astronomers search for life on other planets, one of the first things they look for is water. Finding water does not mean there is life, but it does mean that one of the necessary conditions for life is present. And that is why this discovery has captured the attention of scientists all around the world. Of course, GJ486b is not a habitable planet. It is way too hot, and it is outside what astronomers call the habitable zone. The habitable zone is the region around a star where temperatures are just right for liquid water to exist on the surface of a planet. Not too hot, not too cold. Scientists sometimes call this the Goldilocks zone because the conditions are just right. Earth is in the habitable zone around the sun, Venus is too close and too hot. Mars is too far and too cold. JJ486b is definitely too close to its star to be in the habitable zone. But even though this planet is not habitable, it can still teach us important lessons about how atmospheres form and survive on rocky planets, and those lessons could help us understand other planets that might actually be able to support life. The search for planets outside our solar system, also called exoplanets, has exploded in recent decades. Thanks to missions like Kepler and TESS, scientists have discovered thousands of exoplanets. Some of these planets are gas giants, similar to Jupiter or Saturn. Others are rocky planets, more like Earth or Mars. And a few are right in the habitable zone of their stars, which makes them prime targets in the search for life. But just being in the habitable zone is not enough. A planet also needs to have the right kind of atmosphere. Without an atmosphere, a planet cannot hold on to heat, and any liquid water on the surface would evaporate into space. With the wrong kind of atmosphere, a planet could become a runaway greenhouse like Venus, where temperatures soar to over 800 degrees Fahrenheit, even though Venus is farther from the Sun than Mercury. So understanding atmospheres is absolutely critical. That is where the James Webb Space Telescope comes in. This telescope was designed specifically to study the atmospheres of exoplanets. Unlike previous telescopes, which could only detect the presence of planets, the James Webb Space Telescope can actually analyze the chemicals in their atmospheres. It does this by looking at the light from the star as it passes through the thin layer of gas surrounding the planet. Different chemicals absorb light at different wavelengths, leaving a unique signature in the spectrum. By studying these signatures, scientists can figure out what the atmosphere is made of. They can detect water vapor, carbon dioxide, methane, and even more complex molecules. And with enough observations, they might even be able to detect signs of life like oxygen or methane produced by living organisms. The James Webb Space Telescope is the most advanced observatory ever launched into space. It cost about $10 billion to build and took decades of planning and construction. The telescope is massive, with a primary mirror that is 21 feet across. That mirror is made up of 18 hexagonal segments, each coated with a thin layer of gold. Gold is used because it reflects infrared light extremely well, and the James Webb Space Telescope is primarily an infrared telescope. Unlike visible light, which our eyes can see, infrared light is invisible to us, but it is incredibly useful for astronomy. Infrared light can pass through clouds of dust and gas that block visible light, allowing scientists to see things that would otherwise be hidden. And because light from distant objects gets stretched into the infrared range as it travels through the expanding universe, infrared telescopes like the James Webb Space Telescope can see farther back in time than any other telescope before it. The telescope is located at a special point in space called the second Lagrange point, or L2 for short. This point is about 1 million miles away from Earth, on the opposite side of the planet from the Sun. At L2, the gravitational pull of the Earth and the Sun balance out, allowing the telescope to stay in a stable position relative to both. This location also keeps the telescope in the shadow of the Earth, which helps keep it cool. And staying cool is absolutely essential for the James Webb Space Telescope because infrared sensors need to be kept at extremely low temperatures to work properly. To achieve this, the telescope has a giant sun shield the size of a tennis court. This sun shield is made of 5 layers of a special material that reflects sunlight and heat away from the telescope. Thanks to the sun shield, the side of the telescope facing the sun stays relatively warm, while the side with the instrument stays at about -400 degrees Fahrenheit. That is cold enough to detect the faint infrared glow from distant planets and stars. One of the key techniques the James Webb Space Telescope uses to study exoplanets is called transmission spectroscopy. Let me explain how this works in simple terms. Imagine you're looking at a light bulb through a piece of colored glass. The glass absorbs some of the light, and the color you see depends on what the glass is made of. If the glass is red, it absorbs blue and green light and lets red light pass through. If the glass is blue, it absorbs red and green light and lets blue light pass through. The same principle applies when a planet passes in front of its star. The star is like the light bulb, and the planet's atmosphere is like the colored glass. As the starlight passes through the atmosphere, different chemicals in the atmosphere absorb different wavelengths of light. By analyzing which wavelengths are absorbed, scientists can figure out what chemicals are present in the atmosphere. The James Webb Space Telescope uses two main instruments for this kind of work. The first is NIR-SPEC, the near-infrared spectrograph. NIR-SPEC can look at light from multiple objects at the same time, making it incredibly efficient. It breaks down the light into a spectrum, showing all the different wavelengths and how bright each one is. The second instrument is NIRIS, the near-infrared imager and slitless spectrograph. NIRIS is specifically designed to study the atmospheres of exoplanets. It can take very precise measurements of the light as a planet transits in front of its star, allowing scientists to detect even tiny amounts of chemicals in the atmosphere. In the case of GJ486b, both of these instruments were used and both detected the signature of water vapor. The fact that two independent instruments saw the same thing gives scientists confidence that the detection is real. But detecting water vapor is just the beginning. The next step is to figure out where the water is coming from, and that requires more data. Scientists need to observe the planet multiple times, using different instruments and looking at different wavelengths of light. They also need to create computer models that simulate what the planet and the star should look like under different conditions. If the water is in the planet's atmosphere, the model should show a certain pattern in the data. If the water is coming from star spots, the pattern will be different. By comparing the real data to the models, scientists can figure out which scenario is more likely. This process takes time and it requires a lot of careful analysis, but it is the only way to get a definitive answer. Now let me tell you about the star itself. GJ486 is a red dwarf, which is the most common type of star in our galaxy. Red dwarfs are small, cool, and dim compared to stars like our Sun. They are also incredibly long-lived. While a star like the Sun will burn through its fuel and die in about 10 billion years, a red dwarf can keep shining for trillions of years. That is because red dwarfs burn their fuel very slowly. They are not very hot, and they do not produce a lot of energy, but they are extremely stable. This makes them interesting targets in the search for life because any planets around red dwarfs would have a very long time to develop life. But red dwarfs also have some disadvantages. They are prone to flares, which are sudden bursts of energy and radiation. These flares can be incredibly powerful, and they can strip away the atmospheres of any planets that are too close to the star. So even though red dwarfs are stable and long-lived, they might not be the best places to look for habitable planets. GJ486 is about 26 light-years away from Earth. That might sound like a huge distance, and it is. 26 light-years means it would take light, traveling at about 186,000 miles per second, 26 years to reach us from that star. But in the grand scheme of the universe, 26 light-years is actually pretty close. Our galaxy is about 100,000 light-years across, so GJ486 is practically in our backyard. This proximity is one of the reasons why scientists are so interested in studying the system. The closer a star is, the easier it is to study and the more detailed the data we can collect. And with the James Webb Space Telescope, scientists can now study planets around nearby stars in ways that were impossible just a few years ago. The discovery of water vapor around GJ486b is part of a larger effort to study rocky planets and their atmospheres. For a long time, scientists focused on studying gas giants like Jupiter and Saturn because they are easier to detect and study. But in recent years, the focus has shifted to smaller, rocky planets because those are the ones that are most likely to be habitable. Rocky planets are made of solid material like rock and metal. They have surfaces where liquid water could potentially exist, and they are much more similar to Earth than gas giants are. But studying the atmospheres of rocky planets is incredibly difficult. Rocky planets are small, and their atmospheres are thin. The signals they produce are much weaker than the signals from gas giants. But the James Webb Space Telescope is powerful enough to detect those weak signals, and that is opening up a whole new era of exoplanet science. GJ486b is not the first planet where the James Webb Space Telescope has detected water. In fact, the telescope has found water vapor in the atmospheres of several other planets. One of the most famous examples is WASP-96b, a gas giant about 1,000 light-years away. In 2022, the James Webb Space Telescope captured a detailed spectrum of WSP-96b's atmosphere, showing the clear signature of water vapor along with clouds and haze. This was one of the first big discoveries made by the telescope, and it demonstrated just how powerful the instrument really is. Another example is WSP-107b, a planet that is sometimes called a cotton candy planet because it is so puffy and low in density. The James Webb Space Telescope detected water vapor in the atmosphere of WSP-107b, along with other chemicals like sulfur dioxide. These discoveries are helping scientists understand how atmospheres form and evolve on different types of planets. But perhaps the most exciting water discovery made by the James Webb Space Telescope so far is the planet JJ9827d. This planet is a bit smaller than GJ486b, and it is sometimes called a steam world. Scientists believe that GJ9827d might be a water world, with a thick atmosphere made almost entirely of steam. If that is true, it would be unlike any planet in our solar system. Earth has water, of course, but our atmosphere is mostly nitrogen and oxygen. A steam world would be a planet where water dominates everything. The discovery of GJ9827d has raised some fascinating questions about how planets form and what kinds of environments might exist in the universe. Water is an amazing molecule. It is made of 2 hydrogen atoms and 1 oxygen atom, which is why scientists write it as H2O. Water is incredibly common in the universe. Hydrogen is the most abundant element, and oxygen is the third most abundant. So wherever you find hydrogen and oxygen together, you are likely to find water. But what makes water so special is not just that it is common. Water has unique properties that make it essential for life. For example, water is a liquid at a wide range of temperatures. On Earth, water stays liquid between 32 degrees Fahrenheit and 212 degrees Fahrenheit. That might not sound like a wide range, but it is actually quite unusual. Most substances are either solid or gas at the temperatures we experience on Earth. Water is one of the few substances that can be a liquid, and that is critical for life. Living cells need a liquid environment to carry out chemical reactions, and water provides that environment. Water also has the ability to dissolve a huge variety of substances. That is why scientists sometimes call water the universal solvent. When you add salt to water, the salt dissolves and becomes part of the liquid. The same thing happens with sugar, acids, bases, and many other chemicals. This property is incredibly important for life because it allows nutrients and waste products to be transported inside living cells. Water also has a high heat capacity, which means it can absorb a lot of heat without changing temperature very much. This helps regulate temperatures on Earth and inside living organisms. And water is less dense as a solid than as a liquid, which is why ice floats. This might seem like a small detail, but it has huge consequences. If ice sank, lakes and oceans would freeze from the bottom up, and life in the water would have a much harder time surviving the winter. Because of all these properties, scientists believe that water is essential for life, at least for life as we know it. That does not mean life absolutely requires water. It is possible that life could exist in other solvents, like liquid methane or ammonia. In fact, some scientists have speculated about the possibility of life in the methane lakes on Saturn's moon Titan. But for now, water is the best bet, and that is why detecting water on other planets is such a big deal. It tells us that at least one of the key ingredients for life is present. Now let me tell you about some of the extreme forms that water can take under different conditions. On Earth, we are used to water existing in 3 states: solid ice, liquid water, and water vapor or steam. But under extreme pressure and temperature, water can exist in states that seem almost alien. One of these states is called supercritical water. Supercritical water forms when water is heated above a certain temperature and pressure, specifically above 705 degrees Fahrenheit and a pressure more than 200 times that of Earth's atmosphere at sea level. At this point, the boundary between liquid and gas disappears. Supercritical water is not quite a liquid and not quite a gas. It has properties of both. It can flow like a liquid, but it can also expand to fill a container like a gas. This strange state of matter might exist deep inside some planets, where the pressure and temperature are incredibly high. Another exotic form of water is superionic ice. This is a type of ice that forms under extreme pressure, much higher than anything we experience on Earth. In superionic ice, the oxygen atoms are locked in a solid crystal structure, but the hydrogen atoms are free to move around. This gives superionic ice some very unusual properties. It can conduct electricity like a metal, even though it is solid like ice. Scientists believe that superionic ice might exist inside planets like Neptune and Uranus, where the pressure is millions of times higher than on Earth's surface. If planets like JJ486b have thick water layers beneath their rocky surfaces, those layers might contain superionic ice or supercritical water. Studying these exotic states of matter helps scientists understand what the interiors of planets might look like. The idea that water can exist in so many different forms is one of the reasons why the search for water on other planets is so exciting. Even if we do not find liquid water on the surface of a planet, we might find water vapor in the atmosphere, ice at the poles, or even exotic forms of water deep underground. Each of these discoveries would tell us something important about the planet and its history. For example, if we found ice at the poles of a planet, it would suggest that the planet once had a thicker atmosphere that has since been lost. If we found water vapor in the atmosphere, it might indicate ongoing volcanic activity or other geological processes. And if we found evidence of supercritical water or superionic ice in the interior, it would tell us about the extreme conditions inside the planet. Let me talk a bit more about the habitable zone, because this is a concept that comes up a lot in discussions about exoplanets. The habitable zone is the region around a star where the temperature is just right for liquid water to exist on the surface of a planet. Too close to the star, and the planet gets too hot. The water evaporates, and the planet becomes a dry, barren desert. Too far from the star, and the planet gets too cold. The water freezes, and the planet becomes an icy wasteland. But right in the middle, there is a sweet spot where the temperature is just right. This is the habitable zone, and it is where scientists focus their search for life. The habitable zone is not the same for every star. It depends on how hot and how bright the star is. For a big, bright star like Sirius, the habitable zone is much farther out than it is for our Sun. For a small, dim star like GJ486, the habitable zone is much closer in. That is why GJ486b, despite being very close to its star, is still outside the habitable zone. The star is so dim that even at that close distance, the planet is too hot to have liquid water on its surface. But the habitable zone is not a perfect concept. It is based on some assumptions that might not always be true. For example, it assumes that a planet has an atmosphere similar to Earth's. But if a planet has a very thick atmosphere, like Venus, it could trap heat and become too hot, even if it is in the habitable zone. And if a planet has a very thin atmosphere, like Mars, it might be too cold even if it is in the habitable zone. So being in the habitable zone is a good start, but it is not a guarantee that a planet will be habitable. Another factor that affects habitability is the planet's size and mass. A planet that is too small might not have enough gravity to hold on to an atmosphere. Without an atmosphere, the surface would be exposed to deadly radiation from space, and any liquid water would evaporate. A planet that is too large might have such a thick atmosphere that the surface pressure becomes crushing, making it impossible for life to survive. Earth is just the right size. It is big enough to hold on to a substantial atmosphere, but not so big that the atmosphere becomes oppressive. This is one of the reasons why scientists are so interested in studying super-Earths like GJ486b. These planets are bigger than Earth, but not so big that they become mini Neptunes with thick, hydrogen-rich atmospheres. They occupy a sweet spot in terms of size, and they might be able to support life under the right conditions. The composition of a planet also matters. Rocky planets like Earth are made mostly of rock and metal, with a thin layer of water and atmosphere on top. Gas giants like Jupiter and Saturn are made mostly of hydrogen and helium, with only a small rocky core at the center. Ice giants like Neptune and Uranus are somewhere in between, with a lot of water, methane, and ammonia mixed in with rock and gas. For a planet to be habitable, it probably needs to be a rocky planet. Gas giants do not have solid surfaces where life could exist, at least not life as we know it. Ice giants might have liquid water layers deep inside, but the conditions there would be so extreme that it is hard to imagine life surviving. Rocky planets, on the other hand, have solid surfaces, and if they are in the habitable zone, they could have oceans and continents and all the other features that make Earth such a good place for life. JJ486b is a rocky super-Earth, which makes it an interesting target for study even though it is not in the habitable zone. By studying this planet, scientists can learn about how rocky planets form and evolve. They can learn about how atmospheres are created and destroyed. And they can test the capabilities of the James Webb Space Telescope, figuring out what kinds of signals it can detect and how to interpret those signals. All of this knowledge will be useful when scientists turn their attention to planets that are actually in the habitable zone. And there are plenty of those planets out there waiting to be studied. One of the most exciting targets for future study is a planet called LHS 1140b. This planet is about 40 light-years away, and it is right in the middle of the habitable zone of its star. LHS 1140b is a super-Earth, slightly larger than our planet, and it orbits a red dwarf star similar to GJ486. But unlike GJ486b, LHS 1140b is at just the right distance from its star for liquid water to exist on the surface. Scientists have already started studying this planet with the James Webb Space Telescope, and early results suggest that it might have an atmosphere. If it does, and if that atmosphere contains water vapor, LHS 1140b could be one of the best candidates for finding life outside our solar system. The James Webb Space Telescope will continue to observe this planet over the next few years, and scientists are hopeful that they will find something amazing. Another interesting target is the TRAPPIST-1 system. This system is about 40 light-years away, and it contains 7 Earth-sized planets orbiting a very small red dwarf star. 3 of those planets are in the habitable zone, which makes TRAPPIST-1 one of the most exciting systems for the search for life. The James Webb Space Telescope has already observed some of the TRAPPIST-1 planets, and scientists are analyzing the data to see if any of them have atmospheres. The results so far have been mixed. Some of the planets might have thin atmospheres, while others might have lost their atmospheres completely due to radiation from the star. But the fact that there are 7 planets in one system gives scientists multiple opportunities to study different types of worlds and learn about how planets evolve. The search for life on other planets is one of the most profound questions humanity has ever asked. Are we alone in the universe? Or is life common, scattered across countless worlds in every corner of the galaxy? For most of human history, we could only speculate about these questions, but now, with telescopes like the James Webb Space Telescope, we can actually start to answer them. We can study the atmospheres of distant planets and look for signs of life. We can search for water, oxygen, methane, and other chemicals that might be produced by living organisms. And we can learn about the incredible diversity of worlds that exist beyond our solar system. One of the chemicals that scientists are most excited about is oxygen. On Earth, most of the oxygen in our atmosphere is produced by plants and other photosynthetic organisms. Without life, Earth's atmosphere would have very little oxygen. So if scientists found a planet with a lot of oxygen in its atmosphere, it would be a strong hint that there might be life there. But detecting oxygen is not easy. Oxygen absorbs light at specific wavelengths, and those wavelengths are hard to observe from Earth. But the James Webb Space Telescope is designed to look at exactly those wavelengths, and it might be able to detect oxygen on planets in the habitable zone. If it does, it would be one of the most important discoveries in the history of science. Another chemical that scientists are interested in is methane. On Earth, methane is produced by living organisms, especially bacteria that live in swamps, wetlands, and the guts of animals. Methane is also produced by geological processes like volcanic activity. So if scientists found methane on another planet, it would not automatically mean there is life there. But it would be an interesting clue. If the methane was accompanied by other signs of life, like oxygen or complex organic molecules, it would make the case for life much stronger. The James Webb Space Telescope has already detected methane on several exoplanets. But so far, all of those planets are gas giants or other types of worlds where life is unlikely. The real test will come when the telescope starts studying rocky planets in the habitable zone. The process of searching for life on other planets is slow and painstaking. It requires years of observations, careful analysis, and a lot of patience. But every new discovery brings us one step closer to answering the big question. And even if we do not find life right away, the search itself is teaching us so much about the universe. We are learning about how planets form, how atmospheres evolve, and what kinds of environments might be able to support life. We are discovering worlds that are stranger and more diverse than anything we could have imagined. And we are pushing the boundaries of technology, building instruments that can detect the faintest signals from the farthest corners of the galaxy. The James Webb Space Telescope represents the culmination of decades of work by thousands of scientists, engineers, and technicians. The project began in the late 1990s, and it took more than 20 years to complete. There were countless challenges along the way. The telescope had to be designed to withstand the harsh environment of space, where temperatures swing between extreme heat and extreme cold. It had to be light enough to launch on a rocket, but strong enough to survive the vibrations and forces of launch. And it had to be precise enough to detect the faintest signals from the most distant objects in the universe. All of these requirements pushed the limits of what was technologically possible. One of the biggest challenges was the mirror. The James Webb Space Telescope's mirror is more than 6 times larger than the mirror on the Hubble Space Telescope. But it had to fit inside a rocket, which meant it had to be foldable. The engineers came up with a brilliant solution. They designed the mirror in 18 separate segments that could be folded up during launch and then unfolded once the telescope reached its destination. Each segment is perfectly shaped and coated with gold, and they all work together to create a single, seamless mirror. After the telescope was launched, it took weeks for the mirror segments to unfold and align properly. Ground controllers had to make tiny adjustments to each segment, moving them by fractions of a millimeter to ensure they were all perfectly aligned. It was a delicate and nerve-wracking process, but it worked. The mirror is now performing even better than anyone expected. The sun shield was another major challenge. This enormous structure had to be folded up to fit inside the rocket, and then it had to deploy perfectly once the telescope was in space. The sun shield is made of 5 layers of a material called capton, each layer about as thick as a human hair. These layers are separated by gaps to allow heat to radiate away into space. The sun shield is so effective that the side facing the sun can be more than 200 degrees Fahrenheit, while the side facing away is minus 400 degrees Fahrenheit. That is a temperature difference of 600 degrees across a structure that is only a few feet thick. Deploying the sun shield was one of the most nerve-wracking moments of the entire mission. There were hundreds of mechanisms that had to work perfectly, and if any one of them failed, the entire mission would have been in jeopardy. But everything went according to plan, and the sun shield is now keeping the telescope cool and allowing it to make incredible discoveries. The telescope was launched on Christmas Day in 2021, and it took about a month to reach its destination at the second Lagrange point. During that journey, the telescope went through a complex series of deployments, unfolding its sun shield, extending its secondary mirror, and aligning its mirror segments. Once it reached L2, there were several months of testing and calibration. Scientists had to make sure all the instruments were working properly and that the telescope was focused correctly. In July 2022, the first images from the James Webb Space Telescope were released to the public, and they were absolutely stunning. The images showed galaxies from the early universe, nebulae where stars are born, and detailed views of planets in our own solar system. The quality of the images far exceeded anything that had been seen before, and they gave the world a preview of the amazing discoveries that were to come. Since then, the James Webb Space Telescope has been working non-stop, observing targets all across the sky. It has studied the atmospheres of exoplanets, peered into the hearts of distant galaxies, and captured images of objects that formed just a few 100 million years after the Big Bang. Every week, new data comes in, and scientists around the world are busy analyzing it and making new discoveries. The telescope is expected to keep working for at least 10 years, and possibly much longer. During that time, it will revolutionize our understanding of the universe and answer some of the biggest questions in astronomy. One of the things that makes the James Webb Space Telescope so powerful is its ability to observe in the infrared. Most of the telescopes we use on Earth observe in visible light, which is the light our eyes can see. But visible light makes up only a tiny fraction of the electromagnetic spectrum. There is also ultraviolet light, which has shorter wavelengths than visible light, and infrared light, which has longer wavelengths. Each part of the spectrum reveals different information about the universe. Infrared light is particularly useful for studying cool objects like planets and brown dwarfs, and for looking through clouds of dust and gas. When stars are forming inside dense clouds, visible light cannot penetrate the dust. But infrared light can, allowing us to see what is happening inside. And because the universe is expanding, light from the most distant galaxies gets stretched into the infrared range. So by observing in the infrared, the James Webb Space Telescope can see farther back, in time than any other telescope. The discovery of water vapor around GJ 486b is just one example of what the James Webb Space Telescope can do. But it is an important example because it shows that the telescope can detect even subtle signals from small, rocky planets. In the past, most of the exoplanets that scientists studied were gas giants because they are easier to detect. A gas giant is big and has a thick atmosphere, which makes its signals much stronger. But the planets that are most interesting for the search for life are small, rocky planets like Earth. These planets have thin atmospheres and their signals are much weaker. The fact that the James Webb Space Telescope can detect water vapor around a rocky planet like GJ 486b is a huge step forward. It means that the telescope should also be able to detect other chemicals in the atmospheres of rocky planets, including chemicals that might be signs of life. The study of exoplanet atmospheres is a relatively new field of science. The first exoplanet was discovered in 1995. And for the first decade or so, scientists focused on just finding planets. They wanted to know how common planets are and what kinds of planets exist in the universe. But in the last 10 years or so, the focus has shifted to studying the atmospheres of those planets. Scientists want to know what exoplanet atmospheres are made of, how they form, and whether they can support life. The James Webb Space Telescope is the perfect tool for this kind of work. It can look at dozens or even hundreds of exoplanets, collecting data on their atmospheres and building up a comprehensive picture of what kinds of atmospheres exist in the universe. One of the things scientists have learned from studying exoplanet atmospheres is that there is an incredible diversity of worlds out there. Some planets have atmospheres made mostly of hydrogen and helium, like Jupiter. Others have atmospheres made mostly of carbon dioxide, like Venus. Still others have atmospheres with water vapor, methane, ammonia, and other chemicals. And some planets might not have any atmosphere at all. By studying this diversity, scientists can learn about the processes that create and destroy atmospheres. They can learn about how planets lose their atmospheres over time, and what factors determine whether a planet will be able to hold on to its atmosphere. All of this knowledge is essential for understanding which planets might be able to support life. The question of whether life exists on other planets is one of the most profound questions we can ask, but it is also one of the hardest questions to answer. Life as we know it requires certain conditions. It needs liquid water, a source of energy, and the right kinds of chemicals. But even if all of those conditions are met, life might not arise. The origin of life is still a mystery, even here on Earth. Scientists do not fully understand how non-living chemicals can come together to form living organisms. There are many theories, but no definitive answers. And if we do not fully understand how life started on Earth, it is even harder to predict whether life might exist on other planets. One approach to this problem is to look for biosignatures. A biosignature is a sign of life that can be detected remotely without having to visit the planet in person. On Earth, there are many biosignatures. The oxygen in our atmosphere is a biosignature because it is produced by living organisms. The methane in our atmosphere could also be a biosignature, although it is harder to interpret because methane can also be produced by non-living processes. Other potential biosignatures include complex organic molecules, certain types of minerals, and even patterns in the way chemicals are distributed in the atmosphere. If scientists can detect biosignatures on other planets, it would be strong evidence that life exists there. But finding biosignatures is not easy. Many of the chemicals that could be biosignatures can also be produced by non-living processes. Oxygen, for example, can be produced by the breakup of water molecules in the upper atmosphere. Methane can be produced by volcanic activity. So if scientists found oxygen or methane on another planet, they would need to rule out non-living explanations before they could conclude that life is present. This requires detailed observations and careful analysis. Scientists need to study the entire atmosphere of the planet, looking at all the different chemicals and how they interact with each other. They need to understand the planet's geology and its history, and they need to build computer models that can simulate all of these processes and predict what the planet should look like under different scenarios. The James Webb Space Telescope is giving scientists the tools they need to do this kind of work. With its powerful instruments and its ability to observe in the infrared, the telescope can detect a wide range of chemicals in exoplanet atmospheres. It can measure how those chemicals change over time and how they interact with each other. And it can provide the detailed data that scientists need to build accurate models and test their theories. Over the next few years, as the telescope continues to observe exoplanets, we will learn more and more about what kinds of atmospheres exist in the universe and what conditions might be favorable for life. The study of JJ486b is part of a larger program to observe rocky exoplanets with the James Webb Space Telescope. This program includes observations of dozens of planets ranging from small hot worlds like JJ486b to larger, cooler worlds that are more similar to Earth. By comparing all of these planets, scientists can start to piece together a picture of how rocky planets evolve and what factors determine whether they can hold on to their atmospheres. This is crucial information for the search for life because without an atmosphere, a planet cannot support life as we know it. One of the key questions scientists are trying to answer is whether rocky planets around red dwarf stars can have stable atmospheres. Red dwarfs are the most common type of star in the galaxy, so if rocky planets around red dwarfs can have atmospheres, then there could be billions of potentially habitable worlds out there. But red dwarfs are also very active. They produce powerful flares and bursts of radiation that can strip away the atmospheres of nearby planets. So far, the evidence is mixed. Some rocky planets around red dwarfs seem to have lost their atmospheres, while others might still have thin atmospheres. The James Webb Space Telescope is helping to answer this question by observing many different rocky planets around red dwarfs and seeing which ones have atmospheres and which ones do not. Another important aspect of studying exoplanets is understanding their formation. Planets form from disks of gas and dust that surround young stars. These disks, called protoplanetary disks, are the birthplaces of planets. Over millions of years, tiny grains of dust stick together and grow into larger and larger clumps. Eventually, these clumps become big enough that their gravity starts to pull in more material, and they grow into planets. But the details of this process are still not fully understood. Scientists want to know how long it takes for planets to form, what determines whether a planet becomes rocky or gaseous, and what role water plays in the formation process. Water is thought to be delivered to planets in several different ways. One way is through comets and asteroids. Comets are balls of ice and dust that orbit the sun, and when they crash into a planet, they can deliver large amounts of water. Scientists believe that much of Earth's water might have been delivered by comets billions of years ago. Another way water can be delivered is through the protoplanetary disk itself. If a planet forms far enough from its star where temperatures are cold enough for water to freeze, then water ice can become part of the planet's structure. Later, if the planet migrates inward toward the star, some of that water ice might melt and become part of the planet's atmosphere or surface oceans. Understanding how water is delivered to planets is important for understanding which planets might be habitable. The discovery of water vapor around JJ486b raises interesting questions about how water can survive on a planet that is so close to its star. If the planet is tidally locked and has a scorching hot day side, any water on the surface would have boiled away long ago. So where is the water coming from? One possibility, as I mentioned earlier, is that the water is being constantly replenished by volcanic activity. On Earth, volcanoes release water vapor along with other gases like carbon dioxide and sulfur dioxide. This process, called outgassing, is one of the ways Earth's atmosphere was formed in the first place. If JJ486b has active volcanoes, then it might be releasing water vapor into its atmosphere on a continuous basis. The intense heat from the star would cause this water vapor to escape into space over time, but as long as the volcanoes keep erupting, the atmosphere would be constantly replenished. Another possibility is that the water is not coming from the planet at all, but from the star. Red dwarf stars like GJ486 are known to have dark spots on their surfaces, similar to the sunspots we see on our own sun. These spots are cooler than the surrounding areas, and in those cooler regions, molecules like water vapor can exist. When the planet passes in front of the starlight that filters through to us might be passing through these cool spots, picking up the signature of water vapor from the star rather than from the planet. If this is the case, then the detection does not tell us anything about the planet's atmosphere. It just tells us about the star. This is one of the big uncertainties in the study of GJ486b, and it is why more observations are needed. To resolve this uncertainty, scientists are planning to use a different instrument on the James Webb Space Telescope called MIRI, which stands for Mid-Infrared Instrument. MIRI observes at slightly longer wavelengths than NIRSpec and NIRIS, and it should be able to distinguish between water vapor coming from the planet and water vapor coming from the star. The key is to look at how the water vapor signal changes over time. If the water vapor is in the planet's atmosphere, the signal should be consistent every time the planet transits in front of the star. But if the water vapor is coming from star spots, the signal might change depending on which part of the star the planet is passing in front of. By making multiple observations and looking for these patterns, scientists should be able to figure out where the water vapor is really coming from. This kind of detective work is typical of modern astronomy. Scientists cannot just point a telescope at an object and immediately know everything about it. They have to make multiple observations, use different instruments, and carefully analyze the data. They have to consider all the possible explanations and rule them out one by one until they are left with the most likely answer. It is a slow and painstaking process, but it is the only way to be sure. And in the case of GJ486b, the stakes are high. If the water vapor is really coming from the planet, it would be one of the first detections of an atmosphere on a rocky planet outside our solar system. That would be a huge milestone in the search for life beyond Earth. The history of exoplanet discovery is full of surprises. When the first exoplanet was discovered in 1995, it was not at all what scientists expected. The planet, called 51 Pegasi b, is a gas giant similar to Jupiter, but it orbits incredibly close to its star. It completes one orbit in just 4 days. At the time, this was shocking. Scientists had assumed that gas giants would form far from their stars, where there is plenty of ice and gas to build up a massive planet. But 51 Pegasi b was right next to its star. This discovery forced scientists to rethink their theories of planet formation. They realized that planets can migrate inward after they form, moving from the outer parts of the protoplanetary disk to the inner parts. This process, called planetary migration, is now thought to be very common. Since the discovery of 51 Pegasi b, scientists have found thousands more exoplanets, and each new discovery has brought new surprises. There are planets that orbit 2 stars at once, called circumbinary planets. There are planets that orbit their stars in the opposite direction from the way the star is spinning, called retrograde planets. There are planets that are so hot that their atmospheres are filled with vaporized metals like iron and titanium. And there are planets that are so cold that their atmospheres are made of frozen methane and ammonia. The diversity of exoplanets is far greater than anyone imagined, and it shows just how little we still understand about how planets form and evolve. One of the most interesting types of exoplanets is the hot Jupiter. Hot Jupiters are gas giants that orbit very close to their stars, just like 51 Pegasi b. They are called hot Jupiters because they are similar in size and composition to Jupiter, but much hotter. The temperatures on hot Jupiters can reach thousands of degrees, hot enough to vaporize rock. These planets are fascinating to study because their atmospheres are so extreme. The James Webb Space Telescope has observed several hot Jupiters and found that their atmospheres contain exotic chemicals and weather patterns unlike anything in our solar system. Some hot Jupiters have clouds made of molten rock or vaporized metals. Others have winds that blow faster than the speed of sound. Studying these extreme environments helps scientists understand the physics of atmospheres under conditions that do not exist anywhere in our solar system. Another interesting type of exoplanet is the mini-Neptune. Mini-Neptunes are planets that are larger than Earth but smaller than Neptune. They are thought to have rocky cores surrounded by thick atmospheres made mostly of hydrogen and helium. Mini-Neptunes are very common in the galaxy, but we do not have anything like them in our solar system, so they are still somewhat mysterious. The James Webb Space Telescope is helping to shed light on mini-Neptunes by studying their atmospheres and figuring out what they are made of. Some mini-Neptunes might have so much water in their interiors that they are sometimes called water worlds or ocean planets. If that is true, they would be very different from Earth, with oceans that are hundreds or even thousands of miles deep. The concept of a water world is fascinating. On Earth, the oceans are only a few miles deep and they cover about 70% of the surface. But on a water world, the oceans could be so deep that the pressure at the bottom would turn the water into exotic forms like supercritical water or supersonic ice. There would be no dry land, just an endless ocean stretching from pole to pole. And deep beneath the ocean, there would be a rocky core, perhaps with active volcanoes that release heat and chemicals into the water. Some scientists have speculated that life could exist in the oceans of water worlds, perhaps near hydrothermal vents on the ocean floor. On Earth, hydrothermal vents are home to thriving ecosystems of bacteria, tube worms, and other creatures that do not depend on sunlight. They get their energy from chemicals in the hot water that flows out of the vents. The same thing could be happening on water worlds if they exist. The search for exoplanets has also revealed that planetary systems come in all shapes and sizes. Some stars have just one planet, while others have many. Some planetary systems are tightly packed with planets orbiting very close to each other. Others are spread out over vast distances. And some planetary systems have planets that orbit in very elliptical or eccentric orbits, swooping close to the star and then flying far away. Our solar system is relatively orderly, with planets orbiting in nearly circular paths and spaced out in a regular pattern. But it turns out that our solar system is not typical. Most planetary systems are much more chaotic and diverse. One of the goals of studying exoplanets is to understand how common Earth-like planets are. An Earth-like planet is a rocky planet that is roughly the same size as Earth and orbits in the habitable zone of its star. These are the planets that are most likely to have liquid water on their surfaces and potentially support life. So far, scientists have found a handful of planets that might be Earth-like, but we do not know much about them yet. Most of them are too far away or too faint to study in detail with current telescopes. But the James Webb Space Telescope is changing that. It can study planets that are dozens or even hundreds of light years away, and it can detect the faint signals from their atmospheres. Over the next few years, as more data comes in, we will get a much better idea of how common Earth-like planets really are. There is also the question of how many of these Earth-like planets might actually have life. Even if a planet is in the habitable zone and has liquid water, that does not guarantee that life will arise. Life might be very rare or it might be very common. We simply do not know. On Earth, life appeared relatively quickly after the planet formed. The oldest fossils of simple bacteria are about 3.5 billion years old, and the Earth itself is only about 4.5 billion years old. That suggests that life can arise relatively easily, at least under the right conditions. But it took much longer for complex life to evolve. For most of Earth's history, the only life was simple, single-celled organisms. It was not until about 600 million years ago that complex life, like animals and plants, started to appear. So even if life is common, complex life might be very rare. This is one of the reasons why scientists are focusing on looking for simple biosignatures first. If we can detect oxygen, methane, or other chemicals that are produced by life, that would be a huge discovery, even if the life is just simple bacteria. Detecting signs of complex life, like cities or industrial activity, is probably beyond the capabilities of current telescopes. But detecting simple biosignatures is within reach, and that is what the James Webb Space Telescope is designed to do. Every new observation brings us closer to answering the question of whether life exists beyond Earth. The discovery of water vapor around JJ486b is a reminder of how much progress has been made in the field of exoplanet science in just the last few decades. 30 years ago, we did not know if planets existed around other stars. Now we know that planets are common, and we are starting to study their atmospheres in detail. 50 years ago, the idea of detecting water vapor on a planet 26 light years away would have seemed like science fiction. Now it is routine. The James Webb Space Telescope is pushing the boundaries of what is possible, and it is opening up new frontiers in our understanding of the universe. But the journey is far from over. There are still many mysteries to solve and many questions to answer. One of the biggest questions is whether the conditions that led to life on Earth are common or rare in the universe. Did life arise on Earth because of a lucky series of events, or is life an inevitable consequence of the laws of physics and chemistry? If life is common, then we should find it on many planets. If life is rare, then Earth might be one of the only places in the galaxy where life exists. The answer to this question has profound implications for how we see ourselves and our place in the cosmos. Another big question is what kinds of life might exist on other planets. All life on Earth is based on the same basic chemistry. We all use DNA to store genetic information. We all use proteins to carry out chemical reactions. And we all use water as a solvent. But is this the only way life can work? Could there be life forms that use different chemicals or different solvents? Could there be life that is based on silicon instead of carbon, or life that uses ammonia instead of water? These are questions that scientists are just beginning to explore. By studying the chemistry of other planets, we might find clues about whether alternative forms of life are possible. The study of exoplanets is also helping us understand our own planet better. By comparing Earth to other rocky planets, we can see what makes Earth special. Why does Earth have so much water while Venus is bone dry? Why does Earth have a thick atmosphere with oxygen, while Mars has only a thin atmosphere with mostly carbon dioxide? These are questions that have puzzled scientists for decades, and studying exoplanets is helping to provide answers. For example, by studying how planets lose their atmospheres over time, scientists can better understand what happened to Mars. By studying planets like Venus, scientists can learn about the runaway greenhouse effect and how it might be triggered. All of this knowledge helps us understand our own planet and how to protect it. One of the things that makes Earth so special is its magnetic field. Earth's magnetic field is generated by the motion of molten iron in the planet's core. This magnetic field acts like a shield, protecting the planet from harmful radiation from the sun. Without the magnetic field, the solar wind would slowly strip away Earth's atmosphere, just like what happened to Mars. Mars once had a thick atmosphere and liquid water on its surface, but it lost its magnetic field billions of years ago, and over time, the atmosphere was stripped away. Now Mars is a cold, dry desert. Understanding how magnetic fields form and why some planets have them while others do not is an important part of understanding habitability. Another factor that makes Earth special is its moon. The moon stabilizes Earth's rotation, preventing the planet from wobbling too much. This stability is important for maintaining a stable climate. If Earth wobbled more, the climate would change dramatically over time, making it harder for life to survive. The moon also creates tides in Earth's oceans, which might have played a role in the origin of life by creating tidal pools, where chemicals could concentrate and react. Not all planets have large moons, so this is another factor that might make Earth unusual. But we do not know how important the moon is for habitability. It is possible that planets without large moons could still support life, or it might turn out that having a large moon is essential. These are the kinds of questions that scientists are exploring as they study exoplanets and try to understand what makes a planet habitable. The study of exoplanets is a rapidly evolving field, and new discoveries are being made all the time. Just a few years ago, scientists were celebrating the first detection of water vapor on an exoplanet. Now, the James Webb Space Telescope is detecting water vapor on multiple exoplanets, including rocky planets like JWST. In a few more years, the telescope might be detecting oxygen, methane, and other chemicals that could be signs of life. The pace of discovery is accelerating, and we are living in an incredibly exciting time for astronomy. One of the reasons for this rapid progress is the development of new technologies. The James Webb Space Telescope is the most advanced telescope ever built, but it is not the only one. There are other telescopes being planned and built that will complement the work of the James Webb Space Telescope. For example, the Nancy Grace Roman Space Telescope is scheduled to launch in the next few years. This telescope will have a much wider field of view than the James Webb Space Telescope. allowing it to survey large areas of the sky and discover thousands of new exoplanets. The European Extremely Large Telescope is being built in Chile, and when it is completed, it will be the largest optical telescope in the world. This telescope will be able to study exoplanets in even more detail, potentially even taking direct images of planets in the habitable zones of nearby stars. There are also plans for future missions that could search for life directly. One idea is to send a probe to Europa, one of Jupiter's moons. Europa is covered in a thick layer of ice, but beneath the ice there is an ocean of liquid water. Scientists believe that this ocean might be capable of supporting life. A probe could land on Europa, drill through the ice, and search for signs of life in the ocean below. Another idea is to send a probe to Enceladus, one of Saturn's moons. Enceladus also has an ocean beneath its icy surface, and it shoots geysers of water vapor into space. A probe could fly through these geysers and analyze the water for signs of life. These missions are still in the planning stages, but they represent the future of the search for life beyond Earth. Closer to home, there is also interest in searching for life on Mars. The Perseverance rover is currently exploring Mars and collecting samples of rock and soil. These samples will eventually be brought back to Earth, where they can be analyzed in detail. Scientists are hoping to find signs of ancient life, perhaps in the form of fossilized bacteria or chemical signatures left behind by living organisms. Mars was once a much warmer and wetter planet, and it might have had conditions suitable for life billions of years ago. Even if life does not exist on Mars today, finding evidence of ancient life would be a monumental discovery. The search for life is not limited to planets and moons in our solar system or planets around other stars. There is also interest in searching for technosignatures, which are signs of intelligent life and technology. For example, if an advanced civilization on another planet has developed radio technology, they might be broadcasting radio signals into space. Scientists have been searching for these signals for decades as part of the search for extraterrestrial intelligence, or SETI. So far, no confirmed technosignatures have been found, but the search continues. With new telescopes and better technology, scientists are able to search more stars and cover more of the radio spectrum than ever before. Another type of technosignature that scientists are interested in is the presence of artificial structures in space. For example, if an advanced civilization built large structures around their star to capture energy, those structures might block some of the starlight, creating a detectable signal. This idea was popularized by the star KIC 8462852, also known as Tabby's star, which showed unusual dimming patterns that some people speculated might be caused by alien megastructures. However, further studies showed that the dimming was more likely caused by natural phenomena, like dust or comets. But the idea remains intriguing, and scientists continue to look for unusual signals that might indicate the presence of advanced civilizations. The question of whether intelligent life exists elsewhere in the universe is one of the most profound questions we can ask. If we are alone, it would mean that we are incredibly rare and perhaps special in some way, but it would also mean that we bear a heavy responsibility to preserve life on Earth, because we might be the only conscious beings in the entire universe. On the other hand, if intelligent life is common, it would mean that we are part of a larger cosmic community. It would raise exciting possibilities for communication and collaboration with other civilizations. Either way, the answer would fundamentally change how we see ourselves and our place in the cosmos. For now, we do not have an answer to this question. But every new discovery brings us closer. Every exoplanet we study, every atmosphere we analyze, and every biosignature we search for is a step toward answering the ultimate question: are we alone? The discovery of water vapor around GJ 486b is just one small piece of this much larger puzzle. But it is an important piece because it shows us that the tools and techniques we are using are working. We can detect water on distant planets, we can analyze the chemicals in their atmospheres, and we can start to piece together a picture of what kinds of worlds exist beyond our solar system. The universe is vast, and we have only just begun to explore it. There are hundreds of billions of stars in our galaxy alone, and most of those stars have planets. That means there are potentially hundreds of billions of planets in the Milky Way, and many of those planets might be similar to Earth. Even if life is rare with so many planets to choose from, the odds are good that life exists somewhere out there. And with the James Webb Space Telescope and other advanced instruments, we finally have the ability to search for it. The search for life is also driving advances in many other fields of science and technology. The same techniques that are used to study exoplanet atmospheres are also used in climate science, helping us understand how Earth's climate works and how it might change in the future. The technologies developed for space telescopes are also being used in medicine, communications, and many other fields. And the quest to understand the universe is inspiring a new generation of scientists and engineers who will continue this work in the decades to come. One of the most exciting aspects of the James Webb Space Telescope is that it is just the beginning. The telescope is expected to operate for at least 10 years, and during that time it will make thousands of observations and discoveries. But even after the James Webb Space Telescope reaches the end of its mission, there will be new telescopes to take its place. Technology is constantly improving, and each new generation of telescopes is more powerful than the last. In a few decades, we might have telescopes that can directly image Earth like planets and analyze their atmospheres in exquisite detail. We might be able to see continents and oceans on distant worlds. We might even be able to detect signs of cities or other structures built by intelligent life. The discovery of water vapor around GJ 486b is a reminder of how far we have come and how much farther we have yet to go. It is a testament to human ingenuity and curiosity. We have built machines that can see across vast distances of space and detect the faintest signals from distant worlds. We have developed theories and models that can explain how planets form and evolve, and we have asked big questions about the nature of life and our place in the universe. These are achievements that we should be proud of, and they are just the beginning of a much longer journey. Let me take you deeper into the science behind the James Webb Space Telescope's observations of GJ 486b. When the telescope observed this planet, it used a technique called transmission spectroscopy, which I mentioned earlier. But let me explain in more detail exactly how this works and why it is so powerful. When a planet passes in front of its star, a tiny fraction of the starlight filters through the thin layer of atmosphere around the planet. This is the same light that eventually reaches the James Webb Space Telescope. But as the light passes through the atmosphere, different molecules in the atmosphere absorb specific wavelengths of light. Each molecule has a unique absorption pattern, like a fingerprint. Water vapor absorbs light at certain wavelengths. Carbon dioxide absorbs light at different wavelengths. Methane has its own pattern, and so on. By measuring exactly which wavelengths of light are absorbed, scientists can figure out which molecules are present in the atmosphere. It is like looking at a barcode. Each molecule has its own barcode, and by reading the barcode, scientists can identify the molecule. But there is a complication. The signals from exoplanet atmospheres are incredibly weak. The atmosphere of a rocky planet is very thin, and only a tiny amount of light passes through it. So the absorption signals are very small, often just a fraction of a percent. This is why we need such a powerful telescope like the James Webb Space Telescope. It has to be sensitive enough to detect these tiny signals, and it has to be stable enough to measure them accurately. Another challenge is that the star itself can introduce noise into the measurements. Stars are not perfect, uniform sources of light. They have spots, flares, and other features that can affect the light we see. These features can create signals that look similar to the signals from an exoplanet atmosphere, making it hard to tell them apart. This is exactly the problem scientists are facing with GJ 486b. The water vapor signal they detected could be coming from the planet's atmosphere, or it could be coming from cool spots on the star's surface. To figure out which explanation is correct, scientists need to make more observations and look for patterns in the data. One way to distinguish between these two possibilities is to observe the planet multiple times and see if the signal changes. If the water vapor is in the planet's atmosphere, the signal should be the same every time the planet transits in front of the star. But if the water vapor is coming from star spots, the signal might change depending on which part of the star the planet is passing in front of. Stars rotate, and as they rotate, different spots come into view. By observing the planet over multiple transits and comparing the signals, scientists can figure out whether the water vapor is moving with the planet or with the star. Another approach is to use different instruments that observe at different wavelengths. The water vapor signature shows up at specific wavelengths in the infrared spectrum. But the signal from star spots might show up differently at different wavelengths. By comparing observations from multiple instruments, scientists can get a more complete picture of what is going on. This is why the team studying GJ486b used both NIR-SPEC and NIRISS, and why they are planning to use MIRI as well. Each instrument provides a different piece of the puzzle, and by putting all the pieces together, scientists can solve the mystery. The process of analyzing data from the James Webb Space Telescope is incredibly complex. It involves taking raw data from the telescope, which is just a series of numbers representing the brightness of light at different wavelengths, and turning it into meaningful information about the planet. This requires sophisticated computer algorithms and models. Scientists have to account for all the different factors that can affect the measurements, including the motion of the telescope, the properties of the instruments, and the behavior of the star. They have to calibrate the data to remove any systematic errors or biases, and they have to compare the data to theoretical models to figure out what it all means. The models that scientists use to interpret the data are based on our understanding of physics and chemistry. They simulate what the atmosphere of a planet should look like under different conditions. For example, a model might simulate an atmosphere made mostly of nitrogen, with some water vapor and carbon dioxide. The model calculates how light would pass through this atmosphere and what the transmission spectrum should look like. Scientists then compare the model to the real data and see how well they match. If they match closely, it suggests that the model is a good representation of the real planet. If they do not match, scientists have to adjust the model and try again. This process of comparing models to data is called fitting, and it is one of the most important steps in the analysis. For GJ486b, scientists have created multiple models to explain the water vapor signal. One model assumes that the water vapor is in the planet's atmosphere, and that the atmosphere is being continuously replenished by volcanic outgassing. This model predicts a certain pattern in the transmission spectrum. Another model assumes that the water vapor is coming from cool spots on the star's surface. This model predicts a slightly different pattern. By comparing these models to the real data, scientists can start to figure out which explanation is more likely. But so far, the data is not conclusive. Both models can explain the observations reasonably well, which is why more data is needed. The uncertainty around GJ486b is frustrating for scientists, but it is also a normal part of the scientific process. Science is not about having all the answers right away. It is about asking questions, gathering evidence, and slowly piecing together a picture of how the universe works. Sometimes the evidence is clear and the answer is obvious. But often, the evidence is ambiguous and more work is needed. This is one of those cases. The detection of water vapor around GJ486b is real, but figuring out where it is coming from will take more time and more observations, and that is okay. Science is a marathon, not a sprint. While we wait for more data on GJ486b, let me tell you about some of the other exciting discoveries that the James Webb Space Telescope has made. One of the most impressive discoveries is the detection of carbon dioxide in the atmosphere of an exoplanet called WSP-39b. This was the first time that carbon dioxide had been definitively detected on an exoplanet, and it was a huge milestone. WSP-39b is a hot gas giant similar to Jupiter, and its atmosphere is filled with a variety of chemicals, including water vapor, carbon dioxide, and sulfur dioxide. By studying the atmospheres of planets like WSP-39b, scientists are learning about the chemical processes that occur in hot gaseous environments. Another exciting discovery is the detection of sulfur dioxide in the atmosphere of WSP-39b. Sulfur dioxide is produced by chemical reactions that involve sunlight, and its presence suggests that the planet's atmosphere is actively being altered by the radiation from its star. This is important because it shows that exoplanet atmospheres are not static. They are dynamic systems that change over time in response to their environment. Understanding these changes is crucial for understanding how atmospheres evolve and whether they can remain stable over long periods of time. The James Webb Space Telescope has also made important discoveries about planets in the TRAPPIST-1 system. This system contains 7 Earth-sized planets, 3 of which are in the habitable zone. The telescope has observed several of these planets to see if they have atmospheres. So far, the results have been mixed. Some of the planets appear to have lost their atmospheres, while others might still have thin atmospheres. These observations are helping scientists understand whether Earth-sized planets around red dwarf stars can hold onto their atmospheres in the face of intense radiation from their stars. One of the TRAPPIST-1 planets, called TRAPPIST-1c, has been studied in detail. The observations suggest that this planet probably does not have a thick atmosphere. If it did, the telescope would have detected certain signals in the transmission spectrum, but those signals were not there. This is disappointing because it suggests that the planet might be a barren, airless rock similar to the Moon. But it is also informative because it tells us something about the conditions around red dwarf stars and how they affect planetary atmospheres. The fact that TRAPPIST-1c has lost its atmosphere suggests that the radiation from the star is strong enough to strip away atmospheres from nearby planets. This has important implications for the habitability of planets around red dwarfs. Another planet in the TRAPPIST-1 system, called TRAPPIST-1b, has also been studied. Like TRAPPIST-1c, this planet appears to lack a substantial atmosphere. However, there is still hope for the other planets in the system, particularly the ones that are farther from the star and in the habitable zone. These planets are less exposed to radiation, so they might have been able to hold on to their atmospheres. The James Webb Space Telescope will continue to observe the TRAPPIST-1 system over the next few years, and scientists are hopeful that they will find at least one planet with a substantial atmosphere. In addition to studying exoplanets, the James Webb Space Telescope has also been used to study objects in our own solar system. It has captured stunning images of Jupiter, showing the planet's storms and auroras in incredible detail. ITSET has observed Saturn and its rings, revealing new information about the composition and structure of the rings. And it has studied distant objects in the outer solar system like Pluto and other Kuiper Belt objects. These observations are helping scientists understand the history and evolution of our own solar system, which in turn helps us understand how other planetary systems form and evolve. One of the most exciting aspects of the James Webb Space Telescope is its ability to study the early universe. Because light takes time to travel, when we look at distant objects, we are seeing them as they were in the past. The farther away an object is, the farther back in time we are looking. The James Webb Space Telescope can see objects that are so far away that their light has been traveling for more than 13 billion years. That means we are seeing these objects as they were just a few 100 million years after the Big Bang. This is allowing scientists to study the first galaxies that formed in the universe and learn about how they grew and evolved over time. The telescope has discovered galaxies that are much brighter and more massive than anyone expected. These galaxies formed surprisingly early in the history of the universe, and their existence is challenging our theories of how galaxies form. Scientists are now trying to understand how these massive galaxies could have formed so quickly. It might require new physics or new processes that we do not yet understand. But this is what makes science exciting. Every new discovery raises new questions and pushes us to think more deeply about how the universe works. The James Webb Space Telescope has also been used to study the atmospheres of brown dwarfs. Brown dwarfs are objects that are too big to be planets but too small to be stars. They are sometimes called failed stars because they did not have enough mass to start nuclear fusion in their cores. But they are still interesting objects to study because they have atmospheres that are similar in some ways to the atmospheres of gas giant planets. By studying brown dwarfs, scientists can learn about atmospheric processes that might also occur on exoplanets. One of the instruments on the James Webb Space Telescope that has proven particularly useful is the Near-Infrared Camera, or NIRCam. This instrument is used to take direct images of objects in the infrared. It can capture incredibly detailed images of galaxies, nebulae, and other astronomical objects, but it can also be used to study exoplanets. In some cases, it is possible to directly image an exoplanet, which means taking an actual picture of the planet rather than just detecting its effect on starlight. This is very difficult to do because planets are much fainter than stars, and they are usually very close to their stars, which makes them hard to see. But for certain planets that are large and far from their stars, direct imaging is possible, and NIRCam is helping to make it happen. Direct imaging of exoplanets is exciting because it allows scientists to study the planet in much more detail. Instead of just getting a spectrum of the planet's atmosphere, they can see the planet itself. They can measure its brightness, its color, and how it changes over time. They can study the weather on the planet, and look for clouds, storms, and other features. This is a whole new level of detail that was not possible with previous telescopes. The James Webb Space Telescope is still in the early stages of its mission, but it has already started to produce direct images of exoplanets, and the results are stunning. One of the planets that has been directly imaged by the James Webb Space Telescope is called HIP 6526b. This is a massive gas giant planet that orbits a star about 350 light-years away. The planet is about 6 to 12 times the mass of Jupiter, and it orbits very far from its star, about 100 times farther than Earth orbits the Sun. Because the planet is so far from its star, it is easier to see in direct imaging. The James Webb Space Telescope captured images of this planet at multiple wavelengths, revealing details about its atmosphere and composition. These images are helping scientists understand how massive gas giants form and evolve. The ability to directly image exoplanets is going to be crucial for studying Earth-like planets in the future. While current telescopes like the James Webb Space Telescope are not quite powerful enough to directly image small, rocky planets in the habitable zones of their stars, future telescopes will be. There are already plans for missions like the Habitable Exoplanet Observatory, which is designed specifically to directly image Earth-like planets and search for signs of life. This mission is still in the planning stages, but it represents the next step in the search for life beyond Earth. By directly imaging planets, scientists will be able to study them in much greater detail and look for subtle signs of biological activity. Another important discovery made by the James Webb Space Telescope involves the study of protoplanetary disks. These are the disks of gas and dust that surround young stars and eventually form planets. By studying these disks, scientists can learn about the early stages of planet formation. The James Webb Space Telescope has captured images of several protoplanetary disks, revealing intricate structures like rings, gaps, and spirals. These structures are thought to be caused by planets that are in the process of forming. As a planet grows, it carves out a gap in the disk by pulling in material from its surroundings. By studying these gaps, scientists can infer the presence of planets that are too small or too faint to see directly. One of the most famous protoplanetary disks is around a star called HL Tauri. This disk was first imaged by the ALMA radio telescope, and the images showed a series of bright rings separated by dark gaps. These rings and gaps are thought to be caused by multiple planets forming at different distances from the star. The James Webb Space Telescope has also observed this disk, providing additional details about its structure and composition. By combining observations from multiple telescopes, scientists are building a comprehensive picture of how planets form. The study of protoplanetary disks is also revealing information about where water and other volatile substances come from in planetary systems. In the inner regions of a protoplanetary disk, close to the star, temperatures are too high for water to exist as ice. Water molecules would be in the form of vapor, but farther out from the star, beyond a certain distance called the snow line, temperatures are cold enough for water to freeze. This snow line is important because it determines where icy bodies like comets can form. It also affects the composition of planets. Planets that form inside the snow line are likely to be dry and rocky, while planets that form outside the snow line can incorporate large amounts of ice and become gas giants or ice giants. The James Webb Space Telescope is helping scientists locate the snow line in different protoplanetary disks and understand how it affects planet formation. By studying the distribution of water and other molecules in these disks, scientists can learn about the conditions under which different types of planets form. This knowledge is crucial for understanding the diversity of planets we see in the galaxy and for predicting which planets might be habitable. In addition to studying planets and protoplanetary disks, the James Webb Space Telescope has also been used to study asteroids and comets in our own solar system. These small bodies are leftovers from the formation of the solar system, and they contain clues about the materials and processes that were present when the planets formed. By studying asteroids and comets, scientists can learn about the building blocks of planets and how they came together to form the worlds we see today. One of the comets that the James Webb Space Telescope has studied is called Comet 238P Reid. This comet was observed as it passed through the inner solar system, and the telescope detected water vapor and other molecules being released from the comet's surface. Comets are thought to be reservoirs of water and other volatile substances, and when they crash into planets, they can deliver these substances to the planet's surface. This process is believed to have been important in the early history of Earth, when comets and asteroids delivered water and organic molecules that may have been essential for the origin of life. The James Webb Space Telescope has also been used to study star formation. Stars form inside dense clouds of gas and dust called molecular clouds. These clouds are often opaque to visible light, but they are transparent to infrared light, which is why the James Webb Space Telescope is so useful for studying them. By looking inside these clouds, the telescope can see stars in the process of being born. It can observe the collapse of gas clouds, the formation of protostars, and the birth of stellar systems. These observations are helping scientists understand how stars form and how they evolve over time. One of the most famous star-forming regions is the Carina Nebula, which is about 7,500 light-years away from Earth. The James Webb Space Telescope has captured stunning images of this nebula, showing towering pillars of gas and dust where new stars are being born. The images reveal hundreds of previously unseen stars and protostars, along with jets of gas being ejected from young stars. These observations are providing new insights into the complex processes that occur during star formation. Another fascinating object that the James Webb Space Telescope has studied is the Orion Nebula. This is one of the closest star-forming regions to Earth, and it has been studied extensively by astronomers. The James Webb Space Telescope has revealed new details about the structure of the nebula and the young stars within it. It has detected molecules like water, carbon monoxide, and methane in the nebula, providing clues about the chemistry of star-forming regions. It has also observed protoplanetary disks around many of the young stars, showing that planet formation is already underway in this region. The telescope has also been used to study supernovae, which are the explosive deaths of massive stars. When a star runs out of fuel, it can collapse and explode in a supernova, releasing an enormous amount of energy and creating heavy elements like iron, gold, and uranium. These heavy elements are scattered into space, where they can eventually become part of new stars and planets. In fact, almost all of the elements in our bodies, except for hydrogen, were created in the cores of stars or in supernova explosions. By studying supernovae, scientists can learn about the processes that create the elements and how they are distributed throughout the galaxy. One of the supernovae that the James Webb Space Telescope has studied is SN 1987A, which was first observed in 1987. This supernova occurred in a nearby galaxy called the Large Magellanic Cloud, and it has been studied extensively by astronomers over the past few decades. The James Webb Space Telescope has captured new images of the remnant of this supernova, showing the expanding shell of gas and dust that was ejected during the explosion. The images reveal complex structures and hotspots that are helping scientists understand the dynamics of supernova explosions. The James Webb Space Telescope has also been used to study black holes, which are among the most mysterious objects in the universe. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives, or when matter accumulates in the centers of galaxies. The James Webb Space Telescope cannot see black holes directly because they do not emit light, but it can see the effects of black holes on their surroundings. For example, when matter falls into a black hole, it heats up and emits intense radiation. This radiation can be detected by the telescope, providing clues about the properties of the black hole. One of the most interesting discoveries made by the James Webb Space Telescope is the detection of supermassive black holes in the early universe. These black holes are millions or even billions of times more massive than the Sun, and they exist at the centers of galaxies. The fact that these supermassive black holes existed so early in the history of the universe is puzzling, because it is not clear how they could have grown so large in such a short amount of time. This is one of the big mysteries that the James Webb Space Telescope is helping to solve. By studying these early black holes, scientists are learning about the conditions in the early universe and how the first galaxies formed. The telescope has also been used to study gravitational lensing, which is a phenomenon that occurs when the gravity of a massive object bends the light from a more distant object. This bending of light can magnify the distant object, making it appear brighter and larger than it would otherwise be. Gravitational lensing is a powerful tool for studying distant galaxies and other objects that are too faint to see directly. The James Webb Space Telescope has captured images of several gravitational lenses, revealing distant galaxies that are being magnified by the gravity of intervening galaxy clusters. These observations are helping scientists study the early universe and understand how galaxies evolved over time. One of the most famous gravitational lenses is called the cosmic horseshoe. This is a distant galaxy that is being lensed by a massive galaxy cluster, creating a horseshoe-shaped image. The James Webb Space Telescope has observed this object and many others like it, providing detailed information about the properties of distant galaxies. By studying these lensed galaxies, scientists can learn about the conditions in the early universe and how galaxies have changed over billions of years. The James Webb Space Telescope is also being used to study dark matter, which is a mysterious substance that makes up about 85% of the matter in the universe. Dark matter does not emit, absorb, or reflect light, so it cannot be seen directly, but its presence can be inferred from its gravitational effects on visible matter. For example, galaxies rotate faster than they should based on the amount of visible matter they contain, which suggests that there is additional invisible matter providing extra gravity. By studying the distribution of matter in the universe and how it affects the motion of galaxies, scientists can learn about the properties of dark matter and how it influences the formation of galaxies and other structures. Looking back at the discovery of water vapor around GJ 486b, it is clear that this finding is part of a much larger story. It is a story about humanity's quest to understand the universe and our place within it. It is a story about the development of incredible technology that allows us to see things that were once invisible. And it is a story about the persistence and dedication of thousands of scientists who have devoted their lives to answering big questions. The discovery of water vapor around GJ 486b, whether it comes from the planet or the star, demonstrates the power of the James Webb Space Telescope. It shows that we have the tools to detect even faint signals from distant worlds. It proves that we can analyze the atmospheres of rocky planets and search for the chemicals that might indicate the presence of life. GJ 486b is a world unlike any in our solar system. It is tidally locked, with one side forever baking in the heat of its star, and the other side frozen in eternal darkness. It is a world where the surface is hot enough to melt lead, where volcanic eruptions might be constantly replenishing the atmosphere, and where exotic forms of water might exist deep beneath the surface. And GJ 486b is just one of thousands of exoplanets that we have discovered. Each one is unique. Each one has its own story to tell. Some of these worlds are hot and hellish, others are cold and icy, some are massive gas giants with thick atmospheres, others are small rocky worlds that might be similar to Earth. And somewhere out there, among those thousands of planets, there might be a world where life has taken hold. The search for that world is one of the most important endeavors in human history. Every step we take brings us closer. Every new discovery adds another piece to the puzzle. And every observation made by the James Webb Space Telescope is helping to pave the way for future discoveries. As we continue to explore the universe, we will learn more about where we came from and where we are going. We will learn about the processes that shaped our solar system and our planet, and we will gain a deeper appreciation for the fragility and preciousness of life in the cosmos. The discovery of water vapor around GJ 486b is a small but significant step in this journey. It demonstrates that our telescopes are powerful enough to detect this water, even on distant rocky planets. And it gives us hope that as we continue to study more and more planets, we will eventually find one that has all the right conditions for life. So where do we go from here? The James Webb Space Telescope will continue to observe GJ 486b and many other exoplanets over the coming years. Scientists will analyze the data and refine their models with increasing precision. They will make new observations with different instruments and look for patterns that can help them solve the mystery of where the water vapor is coming from. And eventually, they will have an answer. But even after they have that answer, the work will continue with renewed vigor and determination. There are thousands more planets to study, and each one holds the potential for new discoveries and new insights into the nature of our universe. As we look toward the future, we can be very optimistic about the possibilities ahead. The tools we have developed are powerful beyond anything we could have imagined just a few decades ago. The questions we are asking are profound and incredibly important, and the spirit of curiosity and exploration that drives us forward is as strong as ever. We are living in a golden age of astronomy, and the best is yet to come. The universe is vast and full of wonders. It is a place of unimaginable beauty and complexity. And thanks to instruments like the James Webb Space Telescope, where we are finally able to explore it in ways that were once thought impossible. So the next time you look up at the night sky, remember that among those stars are countless worlds waiting to be discovered. Some might be barren and lifeless, others might be teeming with life. And somewhere out there, perhaps on a planet like JWST or on a world we have not yet discovered, there might be water, the precious substance that makes life possible. This discovery reminds us that the search for life is not just about finding aliens or proving that we are not alone. It is about understanding our place in the cosmos. It is about learning how planets form, how atmospheres evolve, and what conditions allow life to thrive. It is about pushing the boundaries of human knowledge and exploring the unknown, and it is about inspiring future generations to continue this work and carry the torch of discovery into the future. So if you enjoyed learning about the discovery of water vapor around JJ486b and the incredible work being done by the James Webb Space Telescope, I encourage you to stay curious. Keep asking questions. Keep learning about the universe and the amazing discoveries being made every day. And if you want to support this kind of content, please consider subscribing to this channel, hitting the like button, and sharing this video with others who might be interested. Leave a comment below and let me know what you think about the possibility of water on a planet just 26 light years away. Do you think the water is coming from the planet or the star?